Welcome to G Fun Facts Online. Forget the Mars you see in old sci-fi movies. A silent, rust-colored desert under a clear, crimson sky. That static portrait is a fossil. Thanks to our robotic explorers, we now know Mars is a planet of violent, unpredictable, and utterly alien weather. It's a world dominated by winds that whip up continent-sized dust storms, temperatures that swing by hundreds of degrees every day, and ghostly clouds of frozen carbon dioxide. This is the story of modern Mars, a tale of fierce tempests and the science decoding the red planet's violent heart. For centuries, astronomers saw hints of a dynamic climate. In the 17th and 18th centuries, Christian Huygens and Sir William Herschel noted the polar ice caps growing and shrinking with the seasons. Herschel even correctly guessed they were made of ice and that Mars had an axial tilt like Earth's, giving it seasons. By the 1870s, observers spotted, quote, yellow clouds, which were later suggested to be wind-blown dust, our first inkling of the planet's infamous dust storms. But the true nature of the atmosphere remained a mystery. It wasn't until 1947 that Gerard Kuiper's analysis revealed the air was mostly carbon dioxide and far thinner than our own. The space age brought Mars into sharp focus. Mariner 4 flew by in 1965, confirming the thin atmosphere. But the real game-changer was Mariner 9 in 1971. It arrived at Mars to find the entire planet engulfed in a global dust storm. For a month, the surface was completely invisible, a dramatic introduction to the power of Martian winds. When the dust finally settled, Mariner 9 revealed a world of giant volcanoes and canyons, and its instruments gave us our first detailed atmospheric measurements, paving the way for the first weather stations on another world, the Viking landers. Touching down in 1976, the twin Viking landers spent years reporting daily temperature, pressure, and wind speeds. They captured daily and seasonal cycles, the passage of weather fronts, and the onset of those global dust storms. Since then, missions like the Mars Global Surveyor, the Mars Reconnaissance Orbiter, and rovers like Spirit, Opportunity, Curiosity, and Perseverance have built on this legacy, transforming our view from a static globe to a world of breathtakingly complex weather. Today, the Mars Ramin instrument on the Perseverance rover acts as our most advanced Martian weather station, providing daily reports from Jezero Crater, measuring everything from wind speed to the size and shape of dust particles. To understand Martian weather, you have to grasp its atmosphere. It's a whisper with a surface pressure less than 1% of Earth's. Being on Mars would feel like being 45 kilometers, or 28 miles, up in Earth's stratosphere. This thin blanket is 95% carbon dioxide, and it's terrible at holding heat. This leads to shocking temperature swings. Near the equator, a summer day can hit a pleasant 20 degrees Celsius or 70 Fahrenheit, but by nightfall, it plunges to minus 73 Celsius or minus 100 Fahrenheit. The planet's average temperature is a frigid minus 63 Celsius. It's so cold at the poles that the carbon dioxide atmosphere itself freezes, forming seasonal caps of dry ice. This process of CO2 freezing and sublimating drives a massive pressure change, causing the entire atmospheric mass to fluctuate by up to a third over a Martian year. Despite its thinness, this atmosphere is a powerful weather engine, driven by the sun. Uneven solar heating, thanks to Mars' elliptical orbit and axial tilt, creates huge temperature differences between the equator and poles, and between day and night. These temperature gradients are the fundamental force behind the howling winds of Mars. Now, those winds are a study in contrasts. Because the air is so thin, even a high-speed gust would feel like a gentle breeze to a person. But these winds are strong enough to lift the fine Martian dust, sculpting vast dune fields, and, at their worst, engulfing the entire planet. Like on Earth, a large-scale circulation pattern called a Hadley cell moves warm air from the equator towards the poles. Mars also has high and low pressure systems, similar to our cyclones. But one of the most fascinating phenomena is thermal tides. These are global-scale atmospheric waves driven by the daily cycle of solar heating. As the sun heats the daytime side, the atmosphere bulges, creating pressure differences that drive winds. These tides are much stronger on Mars than on Earth, and play a key role in kicking off dust storms. While average winds are a modest 10 to 20 miles per hour, rovers have clocked gusts up to 62 miles per hour. But recent research has shattered our previous assumptions. A 2025 study analyzing thousands of images of dust devils found that surface winds can reach a staggering 160 kilometers per hour, or about 100 miles per hour. That's approaching hurricane-force speeds. These powerful winds are now seen as a major factor in lifting dust into the atmosphere. Among the most captivating weather events are the dust devils themselves. These whirling columns of dust are miniature tornadoes, formed when the ground heats up, creating a pocket of rising warm air that starts to rotate. Martian dust devils can be colossal, reaching several miles high. Their tracks, etched on the surface, are visible from orbit and have become an invaluable tool. By tracking thousands of them in satellite images, scientists have mapped out wind patterns across the planet, revealing a lower atmosphere far more energetic than we ever imagined. But the most dramatic spectacle is the global dust storm. These are tempests on a planetary scale, the largest in the solar system, capable of shrouding Mars in a reddish-brown haze for weeks or months. They typically start as smaller, local storms in the southern hemisphere's spring and summer, when Mars is closest to the Sun. Sometimes, about once every 3 Martian years, these storms explode into a planet-encircling event. The mechanism is a powerful positive feedback loop. Dust lifted into the air absorbs sunlight, which heats the surrounding atmosphere. This heating intensifies the winds, which lift even more dust, creating a runaway effect. Recent studies also link these storms to a seasonal energy imbalance, where a surplus of absorbed solar energy in the southern hemisphere acts as the trigger. The effects are profound. The dust blanket blocks sunlight, causing surface temperatures to drop while the upper atmosphere heats up. For our solar-powered rovers, this can be a death sentence. The lack of sunlight is what tragically silenced the Opportunity rover during the global dust storm of 2018. The fine, abrasive dust also infiltrates and damages equipment, a major hazard for future human missions. While the sky is often a featureless red, Mars does have clouds. They're not like Earth's puffy water clouds, but wispy, delicate structures of water ice or frozen carbon dioxide. Water ice clouds are the most common, similar to our high-altitude cirrus clouds. They form when the tiny amount of water vapor in the air condenses onto dust particles. More exotic are the clouds of dry ice. These form at very high altitudes where temperatures drop to -125°C, cold enough for the CO2 atmosphere to freeze directly. The Curiosity rover has captured stunning images of these eerie, high-altitude clouds. Even more surprising is the discovery of Martian snowstorms. Data from the Phoenix lander and Mars Reconnaissance Orbiter revealed that at night, especially in polar regions, Mars can be hit by violent, localized snowstorms. These aren't gentle flurries, but ice microbursts, strong downdrafts of cold air that carry ice particles rapidly to the surface. It's another example of the planet's unexpectedly dynamic weather. All of this is governed by the seasons. Mars has an axial tilt of 25 degrees, similar to Earth's, giving it 4 distinct seasons. But because a Martian year is nearly 2 Earth years long, each season lasts about 6 months. Crucially, Mars' highly elliptical orbit creates a huge difference between the hemispheres. The planet is closest to the Sun during the southern summer, making for short, hot summers and long, cold winters in the south. The northern hemisphere gets longer, cooler summers and milder winters. This asymmetry is a key driver of the planet's weather, and it's why the massive global dust storms almost always begin in the southern hemisphere. The violent weather of Mars poses huge challenges for exploration. The abrasive dust, the extreme temperature swings, and the low pressure are all major hurdles. But the global dust storms are the biggest threat. Being able to predict them is a top priority for ensuring the safety of future robotic and, eventually, human missions. Studying Martian weather isn't just about understanding another world. It provides a mirror to our own. Mars acts as a natural laboratory, helping us test climate models in a world with a thin, CO2-dominated atmosphere and no oceans. Studying its dust storms helps us understand the role of aerosols in Earth's climate. The story of how Mars may have evolved from a warmer, wetter world to the cold desert of today is a cautionary tale about how fragile a planetary climate can be. Our exploration is far from over. Future missions will continue to unravel the secrets of the red planet's climate. Before astronauts can set foot on Martian soil, we need to master the art of Martian weather forecasting. The silent, static portrait of Mars has been shattered, replaced by the image of a dynamic, breathing, and often violent world. The winds of the red planet have many more secrets to tell, and we are only just beginning to listen.